All right, finally, welcome to Monday and lecture 8. This week is an interesting week in the class. So as always, there is a homework that is due on Thursday and you can turn it in for, I beg your pardon, that is not a bonus points, that is 5 bonus points. That's an error that we'll fix. Lab 4 will be released today as the usual Monday schedule, but there's something new this week. Project 1 will be released along with homework 4 on Friday. Project is a sort of 2-week investigation that you do into a data set. And there is a checkpoint at the end of 1 week where you show progress. You don't have to get things right necessarily. And then the entirety of your investigation you present, you submit 2 weeks after. There'll be a lot more detail about this. You can have partners and so on and so forth. We will also post midterm information. Forgive us for bringing up this awful topic, but our midterm isn't until 8th week. We just like you to know, the details of timing and so on, the alternate time, et cetera, et cetera. So just please keep watching Ed, and this information will go up. I think you'll have noticed that occasionally our recording, in fact, the Zoom lecture gets rather rudely cut off. So to avoid that problem, we are going to schedule the lecture in a new webinar, the link for which we will provide at some time today on Ed. So starting Wednesday, you'll have to change whatever bookmark you have for the link for this lecture to the new one. David, is there something I should add for that? All good?
All good.
All right. So the week, today we'll discuss what is a term that we'll be using throughout the semester, which is distributions. What's a distribution? We will look at categorical distributions, and we'll spend the bulk of the time looking at numerical distributions, which are going to be the main object with which we're going to be working in this class. This lecture tends to go over, so I'm just giving myself a little breathing room. Maybe we'll be finishing up this lecture on Wednesday, and then we'll start in with writing our own functions. You have used many functions. You have used max, sum, you have used the table methods, but it's, after a while you want to write your own because you want to do something particular that is not already in the library. So you'll start writing your own functions, and then on Friday you will use that to make predictions. And then on Friday we'll do something which I'll introduce today. I'll give you a brief introduction to grouping, and on Friday we'll do all the bells and whistles of that. That is our aim for this week. We will try to achieve it. I hope we'll get close. We might not do absolutely everything. Right. So to start out, about distributions, let's just recall some terminology. So an individual is a unit whose features are recorded. So, and what's a feature? A feature is some aspect of that individual. This has multiple names: feature, attribute. In general, it's called a variable because it has different values. So let me just imagine a feature which I think it was in your intake survey, which is handedness. Right? So handedness was a feature. It had 3 values: left-handed, right-handed, and ambidextrous, that is using both. In the individuals were individual students. And each individual had exactly one of those values, right? So that variable, handedness, had multiple values. In that case, it was categorical, but variables can be quantitative as well. We spent some time a couple of lectures ago talking about variables that kind of look numerical, but are actually categorical. Okay, so the variable has different values, and each individual has exactly one value. Now, this is important. If you define your variable so that your values are overlapping, that is, one individual can have more than one, then you need to clean things up a bit before you get to distributions. So a distribution is simply a two-column table. Basically, it is a list of all of the different values of the variable, along with all the frequencies. Now, what does frequency mean? It is the number of individuals that have that particular value. Could also be a percent. So it would be left-handed and the percent left-handed, then right-handed, the percent left-handed, and then both and the percent both. So here's an example of a distribution. So each individual is in exactly one category, and in a distribution, the percents have to add up to 100% because you are essentially splitting the 100% of the individuals into multiple categories. Okay, so now what is this? This is the result of a survey, which was about how often US adults go online. Look at that visualization. It's a modern bar graph, modern bar chart. You know, we have our bars one on top of the other. We have horizontal bars, and you've seen vertical bars. It is increasingly common now to stack the bars up side by side because it is now very easy to include color certainly on the screen and also in print. And so this is a bar chart that has 1, 2, let's see, 3, 4, 5 bars, no, 6 bars. And they are in slightly different shades of blue, right? So the darkest blue is represents the people who use, who go online almost constantly, you know who you are. And then going all the way to the left-hand side, the lightest shade is for those who never go online. That was an interesting number to me, 7% of Americans never going online. This survey was done in the COVID year, that's at 2020, 2021. And the number of assumptions that were made over that period about how easy it was for people to go online really did not include this 7% of people. Anyway, the numbers in the bars represent percents, that is the percents of respondents in those categories. Okay, so the survey was not conducted online. That's an excellent question. Absolutely excellent question. Questions thus far? Has anybody added the numbers in their head and got 100? No? All right, so every now and then you do such a thing and you get 99 or 99 point something, right? It's because some people did not respond and that group is missing. So you have, you know, almost a distribution, but not quite. Also rounding. Yes, thank you, Ashwangit. All right, so here is something that looks very similar. It's also a bar chart, but it's not a distribution. So this is also a survey. This is where parents were surveyed. No, sorry, this is not the parent survey. This is the survey on people quarantining themselves for COVID. So there were a bunch of people who said, I'm not going to quarantine myself. And they were surveyed and they were asked why. And they were asked about reasons that they would not quarantine. And so you have the reasons and the percents who gave those reasons. And now, what do you see? I hope you see a bunch of percents that add up to, I think, quite a bit more than 100. You agree? Right, so what's going on there is that each individual is allowed to provide multiple reasons, right? So you can see that somebody could put in, I'm unable to miss work and I'm unable to arrange childcare, right? So people picked more than one answer, so the bars represent overlapping groups. This thing is not a distribution. It is a bar chart, it gives you some information, but it's not a distribution. I do not actually know whether the respondents were vaccinated because, Gautam, in a distribution, each individual can have must have exactly one value, not more than one, and therefore the percents must add up to 100. More questions? Okay, well, so to visualize a distribution, I need to find, excuse me, I'm going to stop sharing for a second and find my notebook. Here we go. So to visualize a distribution, this is called a categorical distribution. The variables are categories. I just created a data set by copying a table from a survey. This is parents were surveyed in 2020, and they were asked, how confident are you about knowing how much screen time your kid should have? And so the variable is the level of confidence. And so there are three categories, not two, not at all, somewhat, and very. And you have the percents in each category. Each person, each parent could select only one. So if I sum up the percents, what should I get? Yeah, and happily I do get 100. And so the natural way to visualize this is by a bar chart. And now I am going to run this. Parent responses is the name of the table, .bar h for horizontal bar chart. I'm giving it as its argument only the label, the categorical variable, how confident. Where's the other one gone? Is this thing going to run? Not going to run? Yes, going to run? Yes, going to run. If you give it only one variable, then it's going to try to make a bar graph of each of the other columns of the table against this one. We happen to have only one, and it's numerical. It should just work. Okay, there's your bar chart, and in this bar chart, somebody else had done a bunch of work for us. The surveyors had gone and taken the surveys, but they had come back with individual responses for each parent. Yes, it would make multiple charts given more variables. It would, by default, I think it overlays them. So each individual had given one response in one of the categories, and somebody had gone and counted, right? How many individuals, how many parents in each category, and then we have those aggregated data and we drew the chart, but sometimes you have to do the aggregation yourself. And so there, okay, this we've already seen. This is a summary of what we've just done. It is a bar chart, and you choose the order of the bars. But sometimes you have to aggregate. And so we will go back to our movies data set from last time. And there were 200 rows. Each row represented a movie, and each movie had a studio. Right? Each movie was released by a studio, and that was in a column labeled studios. Plural? Labeled studio, yeah. So supposing we want the distribution of studios, let me be clear what that means. We need all the values of the variable. That means we need the name of every single studio. And then we need the number of movies that were released by each of those studios. So if I gave you this table and I asked you how many movies were released by, say, MGM. MGM is the name of a studio, and it's a string in your studio column, then what would you do? If I asked you how many movies were released by studio, what would you do? Would be released by that particular MGM studio. What method comes to mind? Some you could sum, but where is a very good idea. Thank you very much. Where, yes, if you do top movies.where, there, Bennett has the entire line of code typed into chat. Thank you very much. Yes, you would do where, you would first restrict the table to only those who, only the movies released by MGM, and then you would count the number of rows. Terrific. So a combination of where and num rows is what you do. Now, if I asked you, okay, so how many movies were released by Warner Brothers, you would do the same thing again. You would just replace MGM by Warner Brothers, would you not? And you could, for every one of the studios, you could do this repetitive action. And this repetitive calculation is one of the things that computers are very good at. So the data science library, the table, there's a table method called group, which does exactly that, right? So it finds the different values of a studio, and then it groups the rows by those values and counts. And the code looks like this. You simply select your studio column. Yes, you can have more columns. We'll talk about that on Friday. But you simply select your studio column. So you have a 200-line table. There's a row for every movie. The data are just the name of the studio that released the movie, and you run studios.group and table.group, and you have the counts. And so clearly we should do this. Okay, so here is the table. This is a table we saw last time. And we select the studio column. And now we do what the slide said we should do, is we group this this table by its sole column. Yes, you could use a column 0 there as well. And you get, why is the table called studio distribution? Because this is a distribution table. It does exactly what a distribution is supposed to do. It lists the different values of the variable, which is under the studio column, and it says how many were in each, how many were released by each studio. That's in the count column. Yes, this is just an ordinary table. You can relabel columns. So is it necessary to select studio? As I said, you can have multiple columns. We will discuss group in great detail on Friday. This is just an introduction. That is all I'm going to do. What group does is it takes your original table, it groups the rows of that according to the value of your variable and simply counts the rows. It does other things as well, which as you will see on Friday. So if I add this count column, what should I get? I should get the number of what? The column count is automatically created, yes. You should get the number of movies, exactly. And there were 200 of them. And so let's just check that we do get the, yes, we get 200 movies and we're done. So this, what we've got is a distribution, and we would naturally want to draw a bar chart. Okay, so now I want you to look at this. This bar chart, while it is correct, is actually pretty difficult to interpret because the bars are all over the place, but it's because of the order in which they're listed. They're listed, you can see this is in alphabetical order. Why are they listed in alphabetical order? They're listed in alphabetical order because the studio distribution table is in alphabetical order of studio. Why is that? That is because that's what group does. Okay, so run on your question, doesn't it need to sum to 100 to be a distribution? The percents have to sum to 100. These are the counts. This is the number of movies. The total number of movies is 200. If you converted everything to a percent, you would get 100%. So the point I'm making here is that group by default arranges the values, the categories in alphabetical order here. So this is difficult to interpret, so we should sort. And a natural thing to sort by is by the number of movies, the count. So we sort by count in descending order, and then we draw the bar graph, and you can see that Buena Vista and Warner Brothers are at the top. Warner Brothers releases which movies? Do you know? Warner Brothers, yep. Harry Potter as well, yes, exactly. And there's Star Wars and so on. So these are high. Okay, so you have now a visualization of your data. Okay, so we're going to move now to quantitative variables, and there is a clear difference between the job we have to do to visualize a quantitative distribution compared to a categorical one, which is the categorical one. The categories are almost predefined, right? So the names of the studios we already had. But if I take a distribution of times, say, or lengths or ages and so on, there isn't a predefined grouping of those. So that's something that we have to do. And that kind of grouping, when you take your numerical values and you group, that is traditionally called binning. And so, you've seen, if you have exam scores from 0 to 100, there is a very traditional binning in, 0 to 10, then in tens. But somebody made that decision. They didn't have to make that decision, but that's a decision that has to be made. And so binning is just counting how many of the individuals were in each of the ranges, were in each range. And the ranges are called bins. Okay, so a bin is an interval. It starts at one number and it ends at another number, right? So we are going to be defining the bins by their lower bounds. Hold this thought. Think of the bin as an interval from A to B. Okay, and the bins, we are splitting the number line according to these bins. And so supposing we had decided to split the number line in 5 this way, and the list above is our data set. Let me give you some conventions that are going to be used in our binning methods. Every binning method needs to have some conventions about what? About what you do at the edges. All right, and so the convention that we are going to use, a very Pythonic convention, our intervals are going to include the left endpoint, but not the right. Yes, and that is going to be written as Xinyin has described. I'll come to that in a minute. So 165 will go into the 165-170 bin, right? There is a decision that has to be made for the last bin. I'll talk about that later. Okay, so let us start binning these data. 188 is going to go where? Well, 188, I think there's very little doubt about where that's going to go. Okay, 170 is going to go where? Which bin? 170 to 175. Let's see if that works. Yep. Okay. And then we keep going. 189, 163, 183, 171. About these, there is no issue. 185 goes in the bin to its right. 168, 173. Okay. Now look at what's happening there. Don't you see a bar chart developing? That thing looks awfully like a bar chart. What's happening there? So the visualization that we are going to create is something that looks awfully like a bar chart. The one thing, yes, except these bars are of equal width. Why? Because we chose to make the bins of equal width. But we didn't have to choose that. And so when you are describing a numerical distribution in this way, you have to be careful about exactly what the eye sees and exactly what choices you are making in the bins. And so what we're going to do now is take a look at some binning, and then we will come back. Okay, so we are going to look at the movies column with an age column. All right, so we have the year, and what I did was I took 2021, the current year, and I subtracted off the age, the year of release, and I got an age column. So we are going to draw the distribution of the age column, and so I need to know how to bin the ages. A very standard first thing to do is to look at, what is the range, min and max. Okay, so the most recent one was 4 years old in my data set. The most recent one was 4 years old. It's a 2017 data set, I think. and the oldest one was 100 years old. So I'm going to start somewhere. And so what we're going to do is we're going to use the bin method. And apply it to the age column. And we have to specify what the bins are. So my bins are going to be 0, 20, 40, etc., up to 100. And so, okay. So I get a table, and this is a table that we need to carefully understand. Notice that the column 0 just says bin, but it has only one number. That is what the slide meant, but we are going to characterize bins by their left endpoint. So that the left endpoint of the first bin is 0. To understand this 67, you have to look at the second row as well. 20 is the left endpoint of the second bin. Therefore, it is the right endpoint of the first bin. So these three figures are telling us that 67 movies were in the bin 0 to 20. Is that clear? And if it is clear, no, the right endpoint is not inclusive, right? Remember we said that we are going to include the left end, but not the right, very Pythonic. Okay, so could you please tell me how many movies were in the 40 to 60 bin? Chengyan, I'm going to ask you to think of that as 20, please, not 19. Yes, in the 40 to 60 bin, there were 46 movies. You now know how to read this table. Okay, if I add all the counts, how much should I get? I should get 200. Let's just check that. Yep, I haven't lost any movies. Okay, all right. So all the bins except the last one are of the form I include the left, but I do not include the right. So I'm going to look at 40 to 60, and I'm going to do what you said we should do to count how many movies were in that range. I'm just going to do a where and then a numbers. Okay, where the ages are above or equal to 40, and then within that table where the ages are below 60, strictly below 60, and we're going to look at the numbers, and we have 46. That is exactly what is happening here. Okay. Now, this 100 here is actually not the left end of any bin. It is the right end of the last bin. So when you use bin, this last row always has a different interpretation. That last row always gives you the right end of the last bin, and this number here, the so-called count, is always just listed as 0. You can think of that as a placeholder. Now, we do have to decide what happens at the last bin. And for this, it is a good idea to see, was there a movie that was actually 100 years old? There was, because the max of the data was 100. So there is a movie that has age 100. And every binning program has to have some convention. Hold on, Micah. Every binning program has some convention about what happens at the edges. Now, at the left end, we do know that we're including the end of the leftmost bar. At the right end, the convention here is we are actually going to include the right end as well. And now, so the table here says that the bin from 80 to 100 had 6 movies. Let us see if we took all the movies that are at 80 or more years old, but strictly less than 100 years old, would we get 6? No, we get 5. All right. But if we take the movies that are at least 80 years old and at most 100, including 100, then we get 6. So the last bin, the rightmost bin of your binning routine, always has a slightly different status from the previous ones. It includes both its endpoints. This convention is simply necessary when you are, or such a convention is simply necessary when you are binning numerical data. There's something, you have to make some decisions about the endpoints. So let me stop for a second and take questions. That's fine. Okay, so the last count here, the question is, this will always be represented as 0. That's just to have a number in there. And this is telling you that this thing is not a left endpoint. It is the right end of the last bin. That 100 is the right end of the last bin. More questions? So the program, exactly, Danielle, exactly right. The program will run this and will automatically account for the right endpoint if there is a count there. Ashley, last bin will always be inclusive of both endpoints, yes. Okay, now it's a numerical data set. We've been using equal bins. Those are common, but you don't have to. Vincent, there was 100 in the data set. It's right here. Okay, you don't have to split your number line in equal bins. So I'm going to split it in unequal bins. So I'm going to make an array of bin endpoints and try to see what happens. If I do that, and it will bin. It just applies the same criteria. The last bin is always inclusive of both endpoints. If there is not 100 there, it doesn't matter, does it? If there's no data at the end, then it doesn't matter. Okay, and so here also, you have got all 200 movies, and the last bin, 60 to 100, includes the movie that was at 100, right? Below or equal to 100. Okay, so what we're going to do now is, after this discussion about binning, we are going to use a visualization method that uses bins, this binning routine inside it with the same conventions. But before we do that, we have to think about how the eye preserves, how the eye perceives bars. And for this, the example that is really quite revealing was provided by a website called Flowing Data that discusses, data science in general. And this was a graphic that was in the magazine called Gizmodo. At one stage, there was a new iPad, and the new iPad battery was 70% bigger than the old iPad. And this was the graphic that was provided to illustrate that. Now, take a look at that. 70% bigger. Let's just try and remember what that means. 100% bigger means it's twice the size. So 70% bigger means bigger, but not quite twice the size. Now look at the big one. Does that look like not quite twice the size of the previous one? Or is it a lot bigger? It's a lot bigger. To my eye, it's almost 4 times, at least 3. I can certainly fit 2 of these, and then there's room left over. You agree? So there's something wrong with that. And what has happened there is that both axes, the horizontal as well as the vertical, have been increased by 70%. Okay, and so what you are realizing by this picture is what the eye picks up as big is not the individual dimensions, neither just the length, nor just the width, but the area. All right, and therefore, we have what is called the area principle. If you are going to use a 2-dimensional figure to represent a magnitude, then it's the area of that figure that needs to represent your magnitude. All right, so if you represent 20% by one triangle, then you can represent 40% by 2 of those same triangles, but not by doubling both the height and the width. Area should be proportional to the percent of values that you're trying to represent. And so what we're going to do is draw a picture that does that. A histogram displays the distribution of a quantitative variable. There's a bar corresponding to each bin. The area of the bar is the percent of individuals in the bin. And the principal reason for that is, when you have a histogram, or when you have such a display, a bar chart, a histogram, you are displaying the data that you have at hand. but usually you want to use it to say something about the larger world. So you want to be able to compare with other distributions, other histograms, and very often we just want to roughly draw a smooth curve over it. Now take a look at that smooth curve there. Do you see any numbers on any of the axes? Any numbers on the horizontal axis, any number on the vertical? No. Now it happens to be true that the gold shaded area is 68%, roughly 2/3. And though you can't see exactly why that is, surely you can look at that graph and say that that area is at least a half, the gold shaded area. What do you think? Looking good for at least a half? Yeah, okay. Now, so if that is, so just accept that is 68%, we'll have a lot to say about this later. If that's 68%, then what's left over on the two sides? 32%. You can say that, and you didn't need any axes, right? And now the graph looks pretty symmetric, does it not? So what's on the blue tail? 60, exactly, 60. So look at all these calculations that you can do without any axes at all. It is because your eye is seeing areas very clearly and working with areas. And so the diagram that we are going to draw is going to have percents represented by area. Okay, so we are going to draw a histogram, and the method is table.hist of the age column. What I'm going to do because this is going to become important, is I'm going to specify the unit of measurement. The units are years. I'm not actually going to specify bins so that you can see what HIST does by default. Okay, so what HIST does by default is it takes the minimum value, which was 4, and the maximum value, which was 100, and then makes 10 equal width bins in that range, right? And then it draws its figure. The area of each bar is the percent of entries within this bin. The bins have the same conventions as we talked about regarding binning. Okay, so if I look at this and, well, here's my 40, but this edge of the bar is not at 40. I don't know exactly where that is, and that's kind of annoying. I'd like to know where the edges of the bars are, then I can specify my bins, just as we've done before. So I specify my bins here. Equally spaced bins, equally wide bins of with 20, using the bins argument, just as you had for the bin method. And you get a histogram that has 5 bars. And now you know exactly where the edges of the bins are. And I want to emphasize that we have not yet spoken about what the vertical axis represents. The horizontal axis, I think, is pretty clear what it represents. What we're going to do is just confirm that it's the area of the bar that represents the percent of entries, the percent of movies in the bin. Now, for now, ignore units. This bar here, the bar over 20 to 40, that's a rectangle. So its area is its height times its width. Its height is given to me as 1.5 somethings, whatever it is, numerically it's 1.5. What is the width? The width is right endpoint minus left endpoint, so 40 minus 20. And so the area is the height times the width. Do you agree with that arithmetic there in my cell? Okay, so if we run that, we get 30. So the claim is that this bar contains 30% of the data. Well, now we actually binned this data using the same equal bins, and the 20 to 40 bar had 60 movies. And 60 movies as a percent of the total counts. What was the total count? It was 200. 60 movies as a percent of the total count, you have 30%. Okay, so your bar does represent the percent. Okay, why is it 40 to 20, 40 is non-inclusive? Everardo, this is a geometric figure. Okay, we are not looking at the actual ages, we are looking at what is being plotted as a a figure on the number line. So this interval is going from 20 all the way up to 40, 39.999999999. And so therefore the length is 20. And you should not be using a 39 or any kind of discretization here. The interpretation of 30% of the movies were in the bin 20 to 40. Okay. And so now what I'd like to do is take a look at the vertical axis. What is it measuring? Okay, so HIST uses a scale that ensures that the area of the chart adds up to 100%, right? We said that a distribution, in a distribution, the percents have to add up to 100%. In a histogram, the percents are areas, therefore the areas have to add up to 100%. Okay, the horizontal axis is simply a number line. Now, what is the vertical axis? The vertical axis is a rate. It is a percent per year. I'm actually going to go to, well, actually, let's take a look whether I want to go to a demo here or not. Okay. So what we're going to do is we're going to look at this in the context of unequal bins, though, you know, it's exactly the same thing happens if you are using equal bins. This is my bins that we had used before. Binned data were the data binned according to this. If you draw the histogram with these unequal bins, it looks like that. Now look at the 20 to 40 bin, nothing's changed. Its height is still 1.5. Its area is still 30%, it ought to be. What I would like you to do is compare the first bar, that is the 0 to 10 bar, and the last bar, that is the 60 to 100 bar. They are very different widths, okay? But the number of movies is almost exactly the same. 28 in the first one, 27 in the last one. So therefore, the percents are almost exactly the same. Therefore, Sinyin, you are exactly right. The areas are almost exactly the same. And that is kind of visible, right? This bar is maybe a tad taller than the last bar is wide. This one maybe is a tad wider, but the areas are pretty comparable. Do you agree? Area of first bar, pretty comparable to area of second bar. Yeah, okay. What if you had not wanted to bother with this and just plot the counts instead? Now I'm going to do something in the demo that I never want you to do. All right. I'm going to use the bad option to HIST. I am going to draw this by plotting just the counts. Okay, and we're going to see what happens. Okay, if I plot just the counts, then suddenly by looking at this picture, doesn't it look like there's a lot more in 60 to 100 than there are in 0 to 10? There's just more action there, right? Your eye picks up, that's big, but it should be about equal. And what's happened is that plotting the counts has forgotten that the bin size, the two bin sizes are different. So if you use unequal bins, you definitely have to be careful about what you are plotting on the vertical. Even when you have equal bins, it is still a good idea to plot carefully on the vertical axis. So I guess what I'm going to do is look at what these heights are. And so actually, I'm going to do something here that annoys people. I'm going to draw exactly the same histogram again. Normed equals true, Jifeng, you can assume that to mean that's the way to draw a histogram. Normed equals false, I never want you to do, please. Okay, so this is the histogram, and we have all of these bars, and they have heights. So what we're going to do is spend a little time working out how those heights were calculated. Okay, the 40 to 60 bin, you told me some time ago that it contains 46 out of the 200 movies. So 40 46 out of 200 is 23%. The area is 23%. Okay? The bin is 20 years wide. Now, if you have a rectangle whose area is 23 and its width is 20, how are you going to find the height? Area is equal to height times width. Therefore, height is area divided by width. And so by this calculation, you get 1.15. You take the 23, you take the percent, and you divide by the width, and you get the height. And you are dividing percent by years, and so the height has a unit, percent per year, which we will talk about its interpretation quite a lot. Okay, let me just go back to my histogram. We were talking about the 40 to 60 bar. And that height we said was 1.15. That agrees with your picture here. Okay. Why would you ever draw a histogram with unequal bin sizes? Excellent question. Depends on the variable. If you look at the United States education system, right, grades 1 through 5 are elementary school, 6 through 8 are middle school, 9 through 12 are high school, you have 4 years of undergrad, those are unequal. And when you want to summarize those data, you might easily want to use unequal bins. And sometimes you have the same variable, right? So, incomes in one community versus incomes in another community, which have been, two people have drawn histograms and they've used different choices of bins. So you need to be able to compare those, right? And so if you use the calculation that we're doing here, that is just represent percents by areas, then you can do all kinds of calculations. Area in this equation, area represents percents. So it is the percent of movies in that bin, which happens to be 23 in this particular example. So in general, height is percent divided by width. It is the percent of data, but relative to the amount of space in the bin. Kim, yes, this is the difference in the slide right in front of you. Right, because in a histogram, areas are not lengths. Percents are not lengths, percents are areas, and therefore the height has to be calculated accordingly. So the height measures how many movies there are in each bin relative to the width, therefore how crowded the movies are within each bin. And I'll talk a little bit more about that. Let me just see how this works. So area measures percent, height measures something else. For how many individuals in the bin? Well, that is proportional to the percent, so you use area. For how crowded, let's use height, because that's what height measures, how many movies per unit of space on the horizontal axis. Let's just do an example. Okay, so there's our histogram that we have. And I have a question for you. So I want you to compare the 10 to 20 bin, that's this one, with the one next to it. Okay, and which one has more movies? So Sain has a probably. Which one has more movies? The one which has the bigger percent of movies has more movies. Percent is represented by what? Percent is represented by area. So you want the one that has the bigger area. Of those two, which one has the bigger area? 20 to 40. Notice you are hardly using the axis at all. Your eye is just picking that up. Okay, so yes, your answer is 20 to 40 because it has bigger area. But which one is more crowded? What measures density? Well, that is measured by height. Right? And so the bar on the left, the 10 to 20 bar is taller. And what is happening is, I think you have a small number of movies here compared to, actually, I'm going to take 1 second to go back to how many movies there are. The binned data. In the 20, you have approximately 40 movies in the first bar and 60 in the second bar. So let's go back. So you have 40 movies in this first bar, and they have 10 units of space. You have 60 movies in this bar, and they have 20 units of space. So even though there are more movies, they have more elbow room, right? You're imagining them all lining up on this interval here. What the height is measuring is how much jostling and crowding there is on this side. Okay, I am now going to stop. There's a little bit to finish up, and we will finish that up on Wednesday. But now I think you have a sense of what the histogram does. That's funny, Mohammed. Movies need to social distance. Yes, the ones that are distancing beautifully are which ones? That is the one in the last bar, the least crowded. Okay, I will see you all. We will see you all on Wednesday.